Good morning, everyone. My name is Anna Kilian and I am from Mechanical Engineering Faculty of Silesian University of Technology. Today, I want to invite you for the lecture Artificial Intelligence in Practice. With this lecture, we start the week of the Industry 4.0 during the European City of Science Katowice.
It is a little bit more about neural networks. A little bit more about neural networks. So today, during this, the rest of today's lecture, I will talk about a single perceptron, a single neuron, okay, how to classify something using linear function, and also about multiclasses classifiers. Have you heard about linear regression? Linear regression. Have you heard about it? So once you have data, let's say you have a training, training itself, you have data. And on two axes, you have two features. It can be in the form of x1 and y. So for x1 and y of a particular numerical value, it forms roughly something that looks like linear. So the goal of the linear regression, in fact, it's approximation using a linear function of these data points, is to find the best equation that fulfills linear function. So it is an additional coefficient of some value. This is slope of the linear function, and this is equal to x1 value. So the problem is how to find W1 and W0. I have a special purpose. W1 and W0 comes from weights. Not weight for neural network. So we have to adjust some weights in order to have the linear function that minimize the error, the total error between samples and the speaking or linear function. Okay, we would like to minimize the error. So this is the basic problem that we have to investigate. A simple regression is very convenient to define the additional attribute that is called a fake attribute. We call it x0. And x0 is just 1. So even if x0 is 1, always 1. So it looks like x0 is always 1. We call it a bias. Bias. X0, x1 is a feature, and it should lead to some output result equal to 1. The output result y for supervised learning. Do you know the term? Do you understand the term supervised learning? Supervised learning and unsupervised learning. Do you understand the term? The supervised learning is like I am teaching you and you are under my supervision. So supervised learning is when we know exactly what should be at the output of neural network. So it's like the ECG problem. The medicine doctor, has told us that this ECG is for healthy patient, and this one is for ill patient, not healthy, unhealthy patient. So some expert categorize ECG signal according to his knowledge. So we can associate to a particular set of features the appropriate goal. If the goal is known, we have to structure the neural network in such a way that during the training process, we will show the neural network what should be at the output. What should be at the output, and the neural network must adjust all the weights to have at the output appropriate value based on the input features. Okay, based on input features. This is a supervised learning process. Contrary to unsupervised learning, which is Kohonen network. Okay, Kohonen self-organizing math network yesterday on laboratory experiments. I think it was example number 1 or 2. There wasn't any information about the categorization. The neural network itself adjusts weights in order to form everything in groups. So depending on the map, that's why it is called SOM, self-organizing map. SOM, self-organizing map. Kohonen network, SOM, it's the same. It's synonyms. It's just a synonym. Okay? The same name. Different names for the same factor. So I just wanted to say that self-organizing map is unsupervised learning, and here we are talking about supervised learning. Supervised learning. So here is the also description in a very mathematical, clear order. So we have a vector of attributes for each training data points. We see the vector of parameters, weights, W for weights, such that it's a general notation, such that we output the linear relationship between prediction Y and attributes X. It's example for a single attribute, but we can expand everything to have more than one attribute. So you can just imagine that you have a conflict of different data between X2 but the same Y, X3 and the same Y. And all of them in a form of neural network should lead to the reasonable conclusion using linear function. So finally, we should obtain something like given on the slide. So a vector of weights multiplied by the vector of features should lead to one output result. Sometimes we have more than one neuron at the output layer, then it is a little bit more complex because the weight structure is not in a form of vector, but in a form of matrix. Do you know how to multiply different vectors and whether it leads to a number or to a matrix? And how about if we have a horizontal vector multiplied by vertical second value? So we have different results. Okay. So this is why the matrix notation is very convenient. But you have to know the fundamentals of math or algebra. Do you have algebra or just math? Both. Okay. So this is just linear regression. And now perceptron. Perceptron. There is a perceptron in the form of electrical electronic devices. And this is just inspired by a human neuron. It is inspired by human neuron. So here is a human neuron. It contains nucleons, dendrites, cell body or soma. It is called the soma. Here is an axon that connects the nucleons and the dendrites with additional neurons in our brain. Okay, in our brain. There is an axon from another cell, another neuron. Over here we have synapses that connects or just collect data to axon. It works in a form of chemical, physical properties in our brain because it changes some proportion between chemical substances and physical properties. So the energy, the impulses, electrical impulses, and the conductivity of the axon changes. However, right here, the dendrite axon synapses possess some knowledge that has been gained during our training process. The training process means going to school, having our parents just collect some data from grandparents and so on. So everything is inside our brain. So the connection between original human brain neuron and the artificial perceptron, you can see it here. So we have the external elements that are connected with some inputs data. So we feed the data. Here is resistors. You can imagine resistors as elements of different values, like weights. You have weights of different values because all weights for a single neuron are not the same. They are different. And internally, there is a summing function together with some activation function. So whether this neuron is activated or not. I will talk about the activation function a little bit later. So that's how the perceptron is represented, equivalent to the human brain. Maybe it's a simplification, however, it is working. You have seen the robustness, the effectiveness of the neural network yesterday. It works quite well. So the linear perceptron, a single layer perceptron, how does it look like? So on the left-hand side, we have input neurons. Sometimes you have it rotated a little bit, so you have the bottom neurons as the input layer. But let's say, like, do you read from the left to right? How do you know you read from up to bottom? Yes. So it's slightly different. Okay, but in English you read from left to right. So it's like reading a book in English. So you have pictures. It represents a single neuron in input layer. These are neurons in input layer or units. This feature is a number, always a number. Between input layer and the output unit or neuron in the output layer, you have a connection, and the connection is linked with the weight. Do you understand the word weight? Weight. And over here, there is numerical information as a product that comes from the product x0 times w1, w0. It's just a product. So multiplication. x1 weight the xi with wi. Multiplication goes to the output unit. And we are performing, or the neural network is performing this combination for all features. At the input stage, once you configure it at the beginning, the weights are randomly distributed. Randomly. It does not matter what's the weight for a particular connection. But during the training process, we must adjust these weights just to reach at the output the appropriate result. Okay, so it is an iteration process. So the output neuron or output unit, which is here, represents the following function. It's a sum. It's a sum of three products or a number of products. So that's why the notation of a single perceptron is exactly the same like for linear regression. This is the same notation. You can see it here. So linear regression for such a simple perceptron is equivalent. Okay, now we have a break. So generally speaking, neural network learning problem is the adjustment of connection weights to let the network generates the correct prediction on the training data. So this is the general problem. And how to find weights, it's another issue. It's not your task to know how to find the weights, but you have to understand that this is the iteration process, and this is the main strength of the artificial intelligence and the neural network algorithms. So we have a number of different algorithms that will minimize the error at the output, having the correct value at the output, and propagating back, so from the output towards the input feature, error, and based on the error, the weights are adjusted. Based on the error. That's why it is called a gradient descent or the backpropagation algorithm. Backpropagation algorithm. So we propagate back the error that comes from a current particular weights. We calculate the difference between the expected prediction. That's why it is called supervised learning. So we have the expected output and we have the current output the model predicts. There is a difference between the prediction and the expected outcome. So that's how we, or base this number, we calculate and adjust weights towards the input layer. Okay, we don't have enough time to talk deeply about this process, but you must know it exists. It must exist in order to have the model robust. So on the following slides, you have the information, you can read it if you have time. And you have this presentation, you will have this presentation on distance learning platform today. After the lecture, I'm going to prepare the file and send it to Platforma, to distance learning platform. So you can just find all the informations over there. I'm not expecting that you know, for example, by heart, the gradient descent algorithm. It's not necessary. Okay, it's not necessary. You don't have to know, but you have to know that something like that exists. So a number of steps that must be performed: compute error, update neural network weights, like you see here together with one coefficient alpha, also there is an alpha parameter, how fast the training process is. For alpha too small, it leads to the coverage of the problem very slow and may need a lot of training examples and also a lot of epochs. We understand the term epoch. It's like Middle Ages, it's one epoch. Okay, so it contains a number of years. So now, in terms of neural networks, the number of years is the number of samples in the training set. And epoch, one epoch, is when we present all the samples to the input of the neural network. So this is one epoch. So we have to perform a number of epochs, so presents the same samples at the input a number of times, sometimes 20, 30, 50, 100, 200, and so on. So this is the number of epochs. So all the samples from the input data set must be presented, and the weights are adjusted during this process. And we evaluate whether the weights are correct each epoch. So if all samples are presented, not after one single sample or two samples or 10, the whole set of input samples must be presented in order to assess, evaluate whether the neural network is working. Make sense? So now we understand additional element. Sometimes you see in MATLAB on your screen also the information about the epochs. So now we understand epochs means, okay, how many samples we have in an input data set? 20, 100, 8,000. So if the number of epochs is 10, it means the training process is 8,000 input samples multiplied by 10. So 80,000 times altogether. So after 10 epochs, it leads to the error or confusion matrix, the accuracy of the neural network on such a level. So if alpha is too large, it may change weights too quickly if it's too large and spend long time oscillating around the minimum. You also change the parameter, the adjustment of the weights, the correction on a laboratory yesterday. So you change the parameter. You play with a parameter alpha. So you have seen what is the influence. I'm talking about self-organizing map right now. Maybe it's not the same structure of the neural network, because what is the main difference between self-organizing map and perceptron? Self-organizing map, it is unsupervised learning process. Perceptron is a supervised learning process. That's the main difference. It is not exactly the same, but both networks, neural networks, possess the training process. And both training processes contains coefficient that either increase the speed of convergence or decrease the speed of convergence. Like alpha. If alpha is small, then convergence is very slow. We just go very slow in the centers of the data point in terms of self-organizing map component. Very slow. If parameter is very low. If it's high, then it looks like it's trying to find its randomly. It jumps from one point to another one. So this is the for you information that alpha is a little bit too high. Okay, so here is the iteration process for perceptron, how it looks for a single single input, how many iterations you have. The true value of W1 is 0.7, W0 0.3, so the function is 0.3 plus, because W0 is a bias. You understand? The bias. So that's why very often when you read some different information about the perceptron or multi-layer perceptron, you have information about the bias. So the bias is the multiplication by 1. So the weight associated with the bias that shifts the function. It shifts the function. So it does not cross through original coordinates. So it is very convenient because we try to separate, we try to approximate some data points, approximate data. After 2 and after 6 iterations, we can see how the weights are adjusted to a particular value. And for 2 exemplary functions, the red and the blue one, we can see how after some iterations it works. So finally, for the whole data set, the function has been obtained. Here, the red and blue one. As far as I remember, okay, let's check once again in the previous slide. Yes, this is the red one is the ideal one, the true linear function. So the blue one is a function that has been obtained during the training process. You can see how well a single perceptron can deal with linear problem. Because the problem is linear, we try to approximate these data set points using linear function. So the problem can be also solved using standard ordinary methods. Are you familiar with the approximation methods? From numerical analysis, for example, numerical methods. So you know how to find the approximation curve. Linear regression is the approximation of the first order. Okay, this is the first order approximation, and how to find the linear function. So you minimize the error. So instead of having all these points from numerical methods, you can apply neural network. It will deal with this problem. Maybe the curve is not exactly the same, but very often it's just illustration. But very often we don't know what's a particular function that should be applied for such set of features. We don't know it because here we have only one feature. But imagine that you have maybe 50 features. So it's very, very difficult to find it using standard ordinary way. So that's why neural network has its strength to find the linear function in a very similar outcome, very similar error. And sometimes it is much more convenient with neural network, much more convenient because we have data set. We can play with different structures, and we have at the output exactly the same results. You can see it. So some remarks. Let me just read it. Update has many names. Update rule, I mean weights during the backpropagation error from the output layer towards the input one. One of the name is delta rule, gradient rule, or LMS rule. Also in MATLAB environment, if you want to be a little bit more proficient, more effective using MATLAB, there is a toolbox. You can use this toolbox, and you have a number of possibilities, a number of parameters you can adjust, you can set, and you can play with different functions. I'm not talking about our laboratories right now. but maybe after the laboratory. We are on the second or third year? Third year. So in a couple of moments, you will have the final project. Final project. Yes, you have to just do something and you must write your final project in order to defend yourself, that you just gain enough knowledge. Am I right? So you may think, you can think about application of different artificial intelligence method for automation some processes. So in such an order, if you want, if you like it, then I suggest to play with MATLAB and just to familiarize yourself with different features that MATLAB possesses for this particular networks, neural artificial intelligence methods. This is only one small part of this environment, very small part. Update is guaranteed to converge to the best linear fit, so the global minimum of error. So this is, it does not matter what's the rule you apply. Of course, there are more direct ways of solving the linear regression problem. That's what I said a moment ago using the numerical methods. It boils down to a simple matrix inversion not shown during this our lecture. In fact, the perceptron training algorithm can be much slower than the direct solution. So why do we bother with the perceptron? The answer is on a couple of next slides. A couple of next slides. Because till now, I said that it mimics a neuron. I said that in the input are features, and each feature has a weight. And at the output, we have a linear function. It is a linear problem. So how to change it into something that may lead to non-linear conclusion? How to change it? How does a single neuron from biology, the subject in your secondary school? Do you have biology? You don't have biology about human, about different plants, animals in the secondary school or in the primary school? In the high school, biology. So do you have any information about the brain in the high school? Okay, about neurons. So there is also a term that is called a neuron can be activated. A neuron can be activated. So it does not process the product between feature and weight that comes with a neuron, but it also has a function, we call it activation function. If we exceed some amount of the product, the output result, then a neuron is activated. Otherwise, it remains stable. So there is also activation function. Activation function. So the sum that has been calculated previously, the sum, remember the sum between weights and features, now goes to another function, we call it activation function. If the activation function output is positive, then it leads to positive 1 plus 1. If the activation function is negative, then the output is negative 1. So now we have something like a hard limit. It's a hard limit. If the product and the sum is above 0, more than 0, then at the output it is activated, so it leads to the number of 1. If it's below 0, it is not activated, so the output is negative 1. So the activation function. is also included in this process. So here is the activation function F, or the whole activation function of X that combines all information that comes to the neural network. Or in general, it may look like now on the slide. So we have features, weights, adjusted one according to the thickness of the arrow. Let's say the weight number 3 has the highest value. W1 has the lowest, somewhere in between, and W2 is the lowest value. Sum, and right here, I haven't noticed it, haven't introduced here, should be also activation function, and here the decision whether the output is above 0 or not. So, if we take into consideration a single line, so it may perform very well a linear task together with the activation function. At the output, we have either 1 or -1. Sometimes it's a bipolar hard limit function. Sometimes we use unipolar hard limit function. The unipolar means that we have at the output either 0 or 1. So bipolar is -1, 1. Unipolar is 0, 1 at the output. But it is still hard limit function. So it changes, let's say, linear function, linear numerical value from the sum, because we calculate the sum at some stage, into 2 points, either 1 or 0, either 1 and -1. So now it leads to, if we add additional function, to decision loop, because based on input features at the output, we may have, if something belongs to one or another class. So we change a perceptron into something that decides between 2 classes. You understand? So right here is our linear function that we have to adjust. This is linear function. Here are points that belongs to negative class, and here are points that belongs to positive class. It's like ECG, healthy, ill, healthy, ill. So let's say ill are here, healthy are here. Do you know why usually ill are true positive? Because in the most cases, people are healthy. So if we just perform a test, it is better to indicate illness instead of healthy people. So that's why true positive is usually ill. So it is like the test on a production line. Go, no go test. Do you remember from the confusion matrix that I have shown on the last lecture? So go, no go test. It's exactly the same convention. It is better to indicate unhealthy circuit, unhealthy production object instead of healthy. Because we expect that healthy are 99% of the times, and only some chosen are assembled incorrectly. So that's why it is better to indicate only illness or only unhealthy products. So that's why I said that true positive can be on the right-hand side and true negative on the left-hand side. This is also a little bit confusing because I also changed it on the slides and I posted on the distance learning platform. because I had a confusion matrix with 0 and 1. Do you remember? And there was a problem because for you 0 is like a logical something negative, 0, and 1 is positive. So I changed it. And just to indicate it clearly. So binary decision rule. In the space of feature vectors, all samplers at the input are some points. Any weight vector is a hyperplane. One side corresponds to the output of positive one and the other corresponds to negative one, like in the picture. And here are some biases described on also the slide, but I have to also increase my speed because I want to show you something in MATLAB. We can start the process with weights equals to 0. It can be like that, but usually we just associate random numbers, random weights. For each training instance, classify which with current weights for each. So that's what I said a moment ago. During one epoch, you have to present all the data points. You cannot assess the model after presenting only a couple of data points. You have to present all of them. If the output is correct, then we do not change anything. So the weights are correct for a particular point. Otherwise, so if a real class is opposite to the current indication, then we must adjust the weight. We have to change somehow the linear function, the decision rule. We have to change it, adjust the weight. And the process of adjustment also comes from the backpropagation. So we propagate the error. We have some coefficient parameter, whether we do it fast, faster, or slower. Remember, we can increase the number of epochs if the parameter, the changing of the weights, is small. So sometimes we just increase the number of epochs at presentations at the input. So we can wait a couple of more moments in order to have the decision rule designed appropriately. So the binary perceptron, the starting one, here is the classification. Okay, let me just go further. This is the adjustment. Now, separable case. What is a separable case? Do you have an idea? Separable case. What is a separable case? Something is separable. If something is separable, then we can design a linear function that perfectly divides between positive and negative cases. So there is no error between classification. There is no false positive or false negative cases. This is separable case. So if there is no false positive or false negatives, then the case is linearly separable, like written on the slide. Here are some examples. You see features that belong to the process and features belong to the circles, the blue and red one. Everyone can see that there is a line that separates between circles and crosses. It is a separable case. It is a separable case. For such a case, the designing of the linear function and the process may look like here on this couple of pictures. So after some iteration, during the iteration process, a linear function has been designed. Okay, now it has been designed. So we adjust the weights to have separable results. The same occurs if we have a multiclass decision rule. But we must design not only one function, but much more functions. In case of 3 classes, we have to add 2 additional linear functions. And there are 2 cases. It is not indicated directly on the slide, but we have 2 cases. Okay, let's say that we have also one more squares. So it is a class rest separation problem. Class rest means that for each particular class, we have to design a special classification of decision rule. The first one for classes, the second one for circles, the third one for squares, and the fourth one for triangles. It does not matter that it crosses other classes. Does not matter because we separate. Sorry, for triangles, it does not be. It should be. It is not linear separable, so we have to do it in this way. For example, we have to do it in this way. But we have to design such functions in order to separate classes. So how to find the appropriate function is sometimes a challenge. However, the process of finding a linear function is embedded in the neural network backpropagation process. So it's very convenient to use, for example, in terms of 3 classes, 3 neurons. 3 neurons. Okay. So neuron number 1 will represent plus. Neuron number 2, circles, and neuron number 3, minuses. There is a problem if on none of the output we will have the value of 1. On all of them, the number of 0. That's a misclassification. We don't know that it should indicate something like the output. However, we don't see any information. That's one problem. And another problem is that at the output, 2 neurons indicates that this particular feature belongs to the class. Okay, so this is really an issue. But this is an issue for Hartley functions. For Hartley function. Hartley, do you know what is the Hartley function? Do you understand the Hartley? 0, 1, -1, 1. It's a bipolar or uniform Hartley function. Hartley function, in fact, looks like that's a Hartley function, -1 and 1. And here is the feature x. That's a happening function. So if the result is negative, it converts it to the negative point. If the result after summation is positive, then it leads to positive one. That's a happening function. And sometimes the happening function is just 0 and 1. So it is 0 for negative values and 1 for positive. 0. Okay, I have to show you something. I want to show you something. Properties of perceptron. Maybe I have to conclude some elements and then I will proceed to MATLAB, for example. Separability. Separability. True if some parameters that the frame set perfectly correct. Separable problems, non-separable problems. It's much more this one. True, much more realistic. That comes from reality. Very often we have some negative output in this data set. Sometimes we have to take into consideration additional features. For example, if we talk with a medicine doctor, it looks maybe the same, I mean the ECG. However, he takes into account the history of the patient, of the human, and we may say, for this particular case, he's ill, not healthy. So his knowledge is much wider, bigger than features that comes from ECG signal. Okay, so we have to also face with this problem. We have to understand that the data is not everything. The data is a lot, but not everything. That's why the healthy systems, like evaluating ECG, it's only the, do you know the term in situ? In situ test? Like the brief tests. For example, if you enter, I don't know how was it here during the COVID-19, but for example, the in situ test is when you enter the building, you have a self-check during the infrared, and they measure your temperature, and if your temperature is low, then you may enter the building. Okay, so this is the in situ test. If your temperature exceeds some value, then you are not allowed to enter a particular building. So this is in situ. In situ. So for in situ, we have the term telemedicine, from telecommunication and medicine. Telecommunication and medicine. So the medicine means that we can apply some programs based on artificial intelligence in our mobile phones, in our tablets, in our watches, wristwatches, just to briefly in situ evaluate our condition. But the final decision is always by doctor, by an expert. It may indicate some issues with your health. However, you have to go to the doctor because it does not reflect all your conditions. It's only part of your condition. So we may expect during evaluating the data that some points belongs to another class. It is called a non-separable class problem. Non-separable class problem. And the neural network also deals with this problem. So it minimizes, so we say bound, if it's called, or let me translate, say the words about converter. If the training is separable, perceptron will eventually converge binary things. Mistake bound, like here, mistake bound. The maximum number of mistakes in terms of binary things, this is binary thing, here's 0, 1. We have two classes on. Related to the margin or degree of separability. So we try to minimize this linear function in terms of distances of these two elements. So we try to adjust the weight just to have minimum distance between negative value and the positive one. That's accuracy, precision, and recall. The third parameter is called the recall. It is also defined as the ratio of true positives divided by true positives plus false negatives number. So recall is the third coefficient that should be taken into consideration while evaluating the model. So just to have everything on one slide, we can see that relevant elements, false negatives and true positives, are on the left-hand side of the picture. And on the right-hand side, you have false positives together with true negatives elements. So the selected elements are over here. The precision and recall are calculated in the following form. Just to make it in a graphical form. So you must count the number of true positives, false negatives, true negatives, and false positives elements in order to calculate precision, recall, and accuracy. These three parameters. Okay, so let's just calculate using some numbers. You have notebooks, you can find some accuracy, you can find the precision, and you can find the recall. So let's have that we have two labels of 0 and 1 and characters. Remember that true positive, it's a little bit tricky here on this slide. Because usually the positive number is 1. So usually the true positive goes here. If there is a 1 at the input, and also the model indicates 1 at the output. So with a true positive, here is the number for true positive, and over here is the number for true or false negative. So you have the data. I'll give you 2 minutes. I'll give you 2 minutes. In order to calculate the accuracy, precision for the following table. Okay, just take your time and try to find the appropriate result. In a moment, I will going to show you whether your calculations are correct or not. Okay, so take your time. Just to have everything on the slide, let me just show you once again where are the following elements. True labels 0, 1, 0, 1, because it is associated in the same form. So we have 0 and 1, true positives, true negatives, and the predictions 0 and 1, false positives and false negatives. Okay, just to make it clear. So you can substitute the appropriate data into the formula. Appropriate data. Okay, so bear that in mind. Just note it. Okay, just note it. And try to enforce yourself right now to calculate something. You can check your knowledge. You can check yourself whether you can know how to substitute the data. It's a very simple problem. But on the other hand, you have access to distance learning platform. Do you know about this? Have you received an email from Platforma? Yes? Have you received, guys? You should receive an email from distance learning platform. Have you received it? If not, check again, because I would like you in a break between this lecture in a couple of moments, that you will go to Platforma and check whether your email is valid and whether you have access to the distance learning platform. So here is a confusion matrix or classification matrix. It's still the same. Once again, the accuracy, correct predictions divided by all predictions, precision, true positives divided by true positives and false positives, and recall is true positives by true positives and false negatives. And here is our example with the data. So true positives 450, true negatives 1250, 40 is false positive, and 30 is false negative. So who has accuracy calculated? Who has calculated the accuracy? Okay, the last one. The last. Yes, you in white and your colleague on the right, because he's texting with someone. Yes, you are texting. You think we don't see it from this side, but we can see it clearly. You understand that you are texting? You know what you are doing. So try to calculate the accuracy. Okay, who has the result of the accuracy? Is it more than 90%? Definitely it is more than 90. Because it is what should be in numerator. 1250 plus 450 divided by the total number, or in the data set, the total number that comes from the confusion matrix. So it's 96.45%. That's a confusion, that's the accuracy. Okay, how about precision, a second parameter? What numbers should be in numerator? Okay, what should be in numerator? But now it depends whether we indicate zero that meets with zero or one that meets one. But because it depends. Okay, so how we define this matrix, confusion matrix? If the true positive is zero, for example, it's a healthy state, usually a healthy state of any object, automation object, needs to be output as a value of zero. It needs to be correct condition. So if it's a true positive right here, so we have to enter this number in the numerator. About the line, fraction. If the true positive is zero, then we have to put this number here about the functionality. So now it depends on information. Also, it's not given here directly. Information given in the text. So now let's consider automation object. Okay, automation object. So if it's automation object, so we want to have it to check whether it's in a correct state or in a bad damage state. So any damage is usually indicated by a broken number, for example, by a code. If there is no code, like 0, it means everything is perfectly correct. Then it is a good condition, healthy state of an object. So two positives go here. Usually for automation, for the car condition, for any machine. If at the output we have 0, it means it is a healthy, correct condition. Nothing is wrong. So that's why for this example number 1, I consider the 1250 as a true positive. So the precision is calculated as 1250 divided by the total number in row number 1. Total number in row number 1. So the precision is 96.9%. That's also quite high results, but it's good. 1250 versus 40 means that the model is working maybe not very good, but very often good enough. As a first inside or in situ test. Do you understand in situ or just a brief test as a first test before we evaluate something in a more specific condition as an expert? So before we evaluate a model, an object using some very sophisticated measurement devices, we can apply the model with 96 accuracy. It is very often enough. And the third parameter is recall. What's the numerator for a recall parameter? True positives or true negatives? It is a true positives divided by true positives plus false negatives. So there is only one change for a recall. So a recall for example number 1 is 97.6%. So we can expect on the distance learning platform, for example, your own computing matrix, and you must calculate the accuracy, precision, or recall. That's a test. Remember, the distance learning platform generates a unique data set for each of you. So it doesn't mean that all of you will possess exactly the same confusion matrix. That's roughly unbelievable. All of you will have different confusion matrix. So based on your confusion matrix, you must, for example, you are asked to calculate accuracy or precision in point number 1, and you have to face this problem. You must face it, you have to calculate the problem based on your given data set. Okay, so once again, you are not going to have the same confusion matrix, all of you, because it is distributed, the matrix is filled by the system. By the system, it is generated randomly. So we have random data. So I believe it's not so difficult. Now I have changed a little bit the data set, because example number 1 has 40 right here and 250 over here. So I move 100 elements from the false through negatives to false positive. Okay, so once again, try to calculate and compare results. So calculate the accuracy, calculate the precision, and calculate recall. Let's use your notebooks. So now, what is the value of the accuracy? Is it still about 90%? Okay, now it's a little bit less than 90%. In fact, it's 89.17. That's the accuracy of the model. The precision. About precision. Do we still have something like 96%? Or now it drops down? Okay, now it goes down to the value of 89.93. So true positive is the same. However, denominator increases because positive is 140. So 100 more correctly assigned to false positives reduces the accuracy and precision. It reduces significantly, less than 90%. So every 10 data in the data set is classified incorrectly. Statistically, obviously. It is statistics. And the last coefficient, how do we call the last one? Is it correct? Maybe I made a mistake on the slide. If you just have another result, just let me know, so I can correct it. Do you have the same results? Yes? It happens sometimes. If I made a mistake and maybe just copied some data from another slide and you just check it, and you can correct the data, you can correct the result. And the last one is called a recall. So now the numerator contains the three group positives, but denominator remains on the same level because the denominator for recall is two positives plus false negatives. So it remains on the same level. On the same level. So that's a recall. So now we have three parameters. What do I expect? For example, in your laboratory report, in terms of classification codes, there is a number of classification codes. For example, when you must classify using the component network, unfortunately, I don't have enough time to start the component network today. But tomorrow we have this laboratory. We will do some, introduction in the first part of the laboratory together with Dr. Founder. But we have to use these coefficients. Okay, you have to use it. And you must evaluate whether your model is good enough. If you play with different models, you just tune the model. Do you understand the word tune? Tune the model. Tune means you change parameters in order to enhance the model, in order to do the model better. That's the tuning process. So if you play with different models, different structures, different parameters, you should just acquire the confusion matrix and use these parameters, because this is the evaluation of the model, whether it is better to have like 10 neurons in a row or a square matrix of neurons for common networks in a form of 2 times 2 or 5 times 5 and so on. So you must evaluate chosen, let's say, 2 or 3 different models and say that this model is working the best based on the coefficients I am giving you. So this is very simple example because we have only binary problem. So we also call it a go, no go test. Have you ever heard about go, no go tests? It's a critical test on a production line. So we had a go, no go. Go means that we release the product to the market. No go means it has to be thrown away to the bin, the trash bin. Okay, so it is called a go, no go test. You understand? Go, no go. So during the production process, a lot may happen. A lot of things. Something may be damaged. Something can be incorrectly assembled. So in such a case, we have to assess at the end of the production process whether it is good, it has the product good enough condition to release to the market. And the last final test is called a go, no go test. Go, no go. Okay. So usually for go, no go tests, we use a confusion matrix because we have to acquire all the data because we want to do it automatically. So we have to create a model, and the model creates some false positives and false negatives elements. So this is a confusion matrix. However, very often it is very convenient to combine all three elements into one parameter. The one parameter for evaluation of the binary problem is called F-score. F-score. It combines the precision and recall matrix. This is the general formula for F-score. You can see the beta, the Greek letter beta. Greek letter beta. Yes, Greek one. You know Greek letters. Oh, it's a Greek letter beta. So it's the second letter in Greek alphabets. Okay. The first one is alpha. So beta. So beta is involved in this equation in order to calculate the F-score. So just copy this information, copy the formula, because before you calculate the F-score, you have to have precision and recall. And obviously, you have to have also the beta defined. The beta defines like a trade-off, the importance between precision and recall. The trade-off. If beta is less than 1, it focuses, the formula F-score focuses more on precision, but you can see it over here. If beta is greater than less than 1, And if beta is more than 1, it focuses more on recall. Okay? More on recall. Very often we just neglect beta because the most often calculation is for beta equals 1. For beta equals 1. So it is F1. Usually in the problem, you should just observe the question. If the question is calculate F with the index 1, you know that beta is 1. Beta is 1. Sometimes we just substitute by beta 2. What does it mean if beta is 2? It focuses more on recall. And the first possibility is beta equals 0.5. Usually no other possibilities. So either 0.5, the most common is 1, and sometimes 2. So 0.5, 1, and 2. Very rare we use other numbers by beta. Very rare. I evaluated a PhD dissertation last year, and a PhD candidate just uses beta equals 0.8, but it was a very specific program related to agriculture. And he just justified why he uses 0.8 instead of standard beta equals 1. Okay, but on your level, you have to remember index beta should be equal to 1. So you have precision and recall on the same level. Example 3. Okay, so we have a break. Okay, so when I start with after the break, example number 3. Once again, let's focus on binary representation class. Binary. Something belongs to the class or does not belong to it. The goal is to determine whether a cat or a dog is on an image, on a picture. Okay, we have cats and dogs. We have evaluated, created a model, and we want to evaluate its performance using F1 score. Now we understand F1 means that beta is 1. Okay, F1 score. Beta is 1. It means that beta is 1. So we don't have to ask what is the value of the beta. Beta is 1. F1 means beta. In the data set, there is 15 pictures with a cat and 20 images or pictures with a dog. We fit the model again. We check the model using this 15 and 20 pictures. And here is what is the output of the model. And the output, it indicates from the given 15 cat images, the algorithm predicts 9 pictures as a dog. Okay, from 15 cat images, the algorithm predicts 9 as a dog, and from the 20 images of dog, 6 pictures as a cat ones. Okay, just copy the data, try formulate the confusion matrices. Based on this information, you should be able to create a confusion matrix. Okay, so it is really a dog with a cat. If it is a dog, it's really a dog. That's a binary problem. So based on the given data, if there is a cat at the input, so how many times the model indicates it's really a cat? Okay, how many times? Okay, the Y could be Y could parents. It's mobile phone. Because we are also texting. If you cannot see what's on the table, you can see it over here. Astana. Yes. Do you see what is on the table? Can you read it? Just read it. Okay, you are too far, so come here close. Come here close. Take your notes, take your belongings, come here, and you will see everything. I believe you even cannot read anything from the slide. Okay, so who said it should be 6 here? Yes, 6 cats are predicted as cat. Yes. How about dogs? Predicted as dogs. What's the number should be in this place? 14. Yes, 14. That's 20 minus 6. That's 20 minus 6. Okay, because on dog images, 6 has been recognized, predicted as a cat. So 14 are correct. 14. How about cats that are really a dog? So if it's true dog and we indicate cats, what's the number? It is 6 right here. So on the picture, there is a dog, true dog, and we just indicate it as a cat. And the last one, the true cat are recognized as dogs. How many times? How many times? 9. 9 times. Now the predictors I put here. Predictors. The predictors are on the left-hand side. I put predictors on the left-hand side, not the level here. Predictors are here. Here is the true cat and true dog. Okay? So you have to be flexible. You can compose the matrix in a number of different ways. Okay? True cat and true dog predictors on the left-hand side. Is it clear? Is it clear? Okay, so once we have a confusion matrix, we can find coefficients, precision, accuracy, and recall. There are also indication about two positives we might have all the information. Okay, so let's start by calculating the precision. Let's start by calculating the precision. Precision. For F1 score, we have to calculate precision and recall. Accuracy is not necessary. Okay, for F1 score. So let's calculate the precision. How to find the precision based on the given data? It is true positives by true positives plus false positives. Yes, that's the precision. That's a precision. So the precision is 0.5 because it's 6 divided by 12, 0.5. And recall, the coefficient recall, it is true positives by true positives plus false negatives. So it's 6 divided by 9 plus 6. 9 plus 6. So it's 0.4. And finally, the F1 score, by substituting the precision and recall, is calculated right here at 0.44. That's the F1 score. It combines precision and recall. Precision and recall. So you don't have to copy once again the formula for F1 score or F beta. It's enough that you know that F1 by substituting by beta the value of 1 leads your number 2 in front of the fraction, in front of the main formula, where precision and recall are mixed together. Okay, do you have the same result, guys, here in the first rows? Guys, here, the first and second one. Hello. Hello. Do you have the same result? Yeah. Where? Okay, in the phone, and you have the same result? Okay, example number 4. Multiclass F score, multiclass. So a little bit more challenging. Now the confusion matrix really does add additional features. On these features, additional one are birds. So we have cats, dogs, and birds. Okay, 3 different animals. The goal is to determine what is on the image. What is on the image? Whether it's cat, dog, or bird. We want to evaluate the performance of the model, of the AI model, using F1 scoring. The data set contains, once again, 15 features with a cat, 20 images per dog, and also 12 additional features with a bird. So now we have much more data. So now it's not a binary problem. It's not a binary problem. And once we have the model, the classification model, it can be any model like neural network, a neural network that indicates the output, such a feature we have in aggregates, surveys, birds, cats, or dogs. The predictions are 15 cat images, 9 dog features from this and images, and 3 bird ones. So completing cats, the model indicates that the output predicts as the output 9 dogs and 3 birds. So only 3 remaining features left are recognized correctly as a cat. Only 3 from 15. Okay, only 3 from 15 are recognized correctly. That's okay. From 20 dog images, 6 are cats, 4 are birds. So altogether, half of the from 20 dog images are recognized correctly. So 10 are correct. And 12 bird images, 4 dogs, 2 cats, and remaining 6 are birds. Remaining 6 are birds. Okay, remaining 1. So how about confusion matrix? We must create a confusion matrix that will consist of dog, birds, and cats. What is that? Just to be consistent with my information on other slides, dog, birds, and cats. Okay, so dogs, birds, and cats. Here are predictors, and here are true states. So true dog, true birds, and true cats. Let's try to compose the confusion matrix. So dogs that are dogs are 10. So the diagonal of the confusion matrix is quite simple to find because it's 10 birds of birds. It's 6 birds, cats that are cats are 3. That's a very simple numbers here on the diagonal of the matrix. Now, we have to find whether the true dogs are predicted as a bird. So the second information here, how many images that contains dogs are predicted as birds? 4. How many dogs are predicted as cats? 6. How many birds are predicted as dogs? Birds as dog. 4. And how many birds are predicted as cat? That's 2. Now we have to consider cats. How many cats are dogs? 9. And cats as a bird, 3. Let's check if it's right. Okay, I hope now you understand how to fill the table. And it does not matter whether you have true labels here and predicted one here. You have to know how interpret the information from the text. Okay, the interpretation is very important. So don't fix your mind that the prediction is always here or always here. It always depends. Sometimes we just put predictors. It depends on the literature. It depends on different websites. So sometimes the predictors are over here, sometimes are here. Does not matter. You have to know how to fill the table. That's the most important. Because we are asked here to calculate the F1 score, so it's not so easy to find F1 for multiclass problem. It's not a binary problem. For binary problem, you can find the precision and recall very easy. Now it's a multiclass problem. Do you have any idea how to find the F1 score? We have 2 possibilities, micro and macro. 2 possibilities. It's a micro F1 score and macro F1 score. Micro and macro. Let's focus on the second one, macro F1 score. Macro one. And here is the macro F1 score calculated. So first of all, we have to calculate the dog, bird, and cat precisions. Okay, precision. So what is the dog precision? It's a true positive for a dog, so it's 10, divided by all numbers that goes to, that indicates a dog. From that indicates other elements if at the input is dog. So we have 10 plus 4 plus 9 in a row. It is in a row. 10 plus 4 plus 9. So true positive. False positive that comes from birds. And false positive that comes from cats. Because from cats, okay, I think that is explaining. No, it's predictable. That's correct. It's not. That's correct. 9. So false positive as cat is 9. False positive for bird is 4. And true positive, the same number, numerator and denominator is 10. So that's the precision for dog. That's a precision. You got it? For bird. True positive for bird is 6. False positive for dog. False positive for dog in this column is 4. And false positive for cat is 3. So the predicted bird is 4 if at the input is dog, and predicted bird from images that contains cat is 3. That's a bird precision. Cat precision, it is calculated in the same way. So 3 numerator divided by all predictions that comes from all images. Even if it's a dog or cat or bird, sometimes the model predicts it is a cat. So false positive and false positive for cat and false positive for bird. So precision for cat is 0.27. It's 0.27 from our data set. Do you understand? Do you understand the formula here for multiclass problem? And macro precision is the average of these three precisions. That's a macro precision. That's the average of three elements. So we add precision, dot precision, bird precision, cat precision, and divide by 3. Is it clear? So that's the macro precision. And the recall for dot, bird, and cat are calculated according to the similar formulas. And we have to calculate the average recall for the multiclass problem. Average recall. Here are all formulas. Dot recall. So true positive for dot. Divided by true positive. So from the dot images, we have 20 images. In fact, here in the denominator, there is 20 images of dot. 20 images of dot. Over here is 12 images of at the input of bird. Right here is 15 images of bird. So that's the input data in denominator. In numerator, it's a true positive from this amount of data. It should be a dot on these pictures, but it indicates a dot only half of the cases. That's a recall. Bird, also 0.5, cat, unfortunately, only 20%. That's a recall. The average recall, so the macro recall score is the average of 3 recalls. And the macro F1 score is a macro precision multiplied by a macro recall divided by the sum of both, like F1. Questions? Do you hear me? Yes. It's clear. Do you have questions? Well, calculations are not very complex. Do you agree? Calculations are quite simple, but the understandable of the problem sometimes is challenging. Where to put the appropriate data? This is the main challenge. Okay, so you don't have to be very we don't have to very sophisticate mathematics here, but we have to know how to interpret the appropriate data and where to put the data. So we add some reason, some knowledge. Calculations are very simple. And now micro F1 score evaluation. So we evaluate F1 in a micro scale. So that's a different approach, macro and micro. Micro precision score, You can see what is the formula for micro precision. I especially add some brackets that you can see that what is in the denominator in fact. So altogether, precision score is the sum of the diagonal elements divided by true positives of all images. True positive of all images. So in fact, in denominator, what do we have? The sum that comes from the whole matrix. Okay, 10 plus 4 plus 9, 6 plus 4 plus 3 comes to 6 plus because it's so that's 0.4. Micro recall score. You understand why we have three numbers here? Because false before dot are two numbers, not only one. So we have to add them together. So that's why we have three numbers, but it looks like two elements here in the general order. But false positive for dots, it's for dot, it's 4 and 9. So that's why we have to calculate the micro total precision score in that way. Micro recall score, true positive for dot, true positive for belt, true positive for top, and the denominator, all the numbers that comes associated with false negative results. False negative results. So the F1 score for micro precision is 0.401. So 0.401. Comparing to the previous one, it's a little bit greater than the first one, micro and macro. But both of them evaluates the model accuracy, the effectiveness of the model. So just to conclude this part of the lecture for the multiclass F-score problem, you are familiar with the micro and macro F-score calculations. The algorithm for multiclass classification has some points. So you have to get predictions from your model. So create a confusion matrix. You must pick the appropriate data from the model. You have to associate true image or true information from the data set, and also the predictors, what is at the output. After that, you usually use the machine learning library. It can be Python. Do you know anything about Python? Python, the language. Have you had Python? Yeah. Okay, so we are familiar with the Python. How about MATLAB environment? Do you know MATLAB? You know MATLAB. Okay, so it shouldn't be any problem to find the correct solution tomorrow on our laboratory, because we start with the MATLAB environment. We prepared some tasks for you, and we will explain everything on the laboratory exercises. Okay, other parameters that should be taken into consideration while evaluating the model. Regression matrix. The first one is explained variance, compares the variance within the expected outcomes and compares that to the variance in the error of the model. The matrix especially represents the amount of variation in the original data set that the model is able to explain. And here is the formula. We will see using the example later how to use the formula. Now you have to just remember there is a regression matrix, and for a regression matrix explained variance. Mean square error, as a very well-known parameter, mean square error value. It is defined as the average of squared differences between the predicted output and the true output. Squared error is commonly used because it is agnostic to whether the prediction was too high or too low. It just reports that the prediction was incorrect. And very often, the most important are R-square coefficient. R-square coefficient. Also, Python and MATLAB offers R-square that represents the proportion of variance in the outcome that the model is capable of predicting based on its features. So R-square usually should be a linear function, R-square, in terms, for example, of neural networks, in terms of the classification problem or regression problem, R-square. That's the most important value. What is a bias? What is a variance? There is a very nice slide where low bias and high bias are explained, comparing to the goal. The goal is the middle of, there is a target. So high or a low bias, whether means that if we are close or far from the goal. And once we have bias, we can say also a little bit about a variance. Variance means what's the distribution of the goals, of the targets. The low variance means that they are roughly in the same place. High variance means that it is distributed somewhere else. So we have quite high mean square error comparing to the low variance. So bias is a deviation of the average output of the trained algorithm from the prediction of the ideal algorithm. The ideal one, for example, is the target in red. The target in red. And a variance is a scatter of the predictions of the trained algorithm related to the average prediction. Okay, that's a variance. That you see all low and high variance. So two parameters, bias and variance. Two parameters related to model. In terms of neural networks, you will hear a number of times such a word like underfitting or overfitting. Under and overfitting. So if we take into consideration bias and variance, we can just formulate some statements. The model with too much pre-built structure, which limits the model's ability to learn from the examples. For example, if train a linear model on an exponential data set, okay, linear model on an exponential data set, model is biased by the pre-imposed structure and relationships. So we cannot just use the model with a structure of the linear function, it is a linear model, and the data set at the input are normally on the exponential form. They are exponential. It's impossible to learn linear model using exponential data. Okay, we have to adjust the model. We have to use another model just to have better one. If it does not fit, then we can expect a very high bias. Model with high bias pay little attention to the data set presented. This is also known as underfitting. Model with high bias. This is underfitting. So we can, for example, see here. Here are samples in the data set. And here is the linear model. For example, we would like to approximate these points, samples, using linear function. That's impossible. Okay? Because linear function has its limitation. So we can adjust it somehow, but if we add even 1 or 2 points, it has rather no influence on the slope of the function. It has no influence. So the model is constructed incorrectly, is designed incorrectly, it is split from the different models in a wrong way. We have to choose another model, more complex model. So this is called underfitting. Sometimes, for example, in terms of neural networks, like a supervised neural network, underfitting exists if you perform too few efforts. You perform a training process in a loop. The training process takes time. We just provide the whole data set in a number of efforts. We call it efforts. It's an iteration process, a number of efforts. If the number of efforts is very low, sometimes means 50, sometimes 100, it's still very low. We expect that the neural network is underfitted. So it will possess high bias. So underfitting, another statement, it is also possible to bias a model by trying to teach it to perform a task without presenting all of the necessary information. So if you don't shuffle the input data, you have to shuffle the data. You must provide the data randomly at the input in order to enhance the model capability. So if it's not enough information or not enough iteration, we can expect underfitting. If we know that constraints of the model are not biasing the model's performance yet, we are still observed signs of underfitting. It's likely that we are not using enough features to train the model. So if the model has very low accuracy precision as the output of the input value, probably we have too few data, or the features that comes from the data are not enough to create good enough model. It is not enough. Okay, we have to find additional features, additional elements that should be provided at the input of the model. So all these elements must be also kept in mind. So contrary to underfitting is termed for overfitting. So sometimes there is not enough data in the data set, but sometimes we have so many data that we can overfit the model. That's the additional edge of the fitting, under and overfitting. Some statements. If the model learns too much from the training data, then we say it is overfitted. The model captures the noise in the data in addition to the signal. Okay, that's also a true statement, because the data that comes from the environment very often is distorted. It's distorted by additional noise. This is caused by fluctuations in the model that does not represent the true trends. The model has high variance. The model does not generalize well because it pays too much attention to the training data without consideration for generalizing the new data. The model has been overfit to the training data set. And here is an example. The approximation of the same samples using, let's say, neural network, it should approximate, but it looks like interpolation, more like interpolation, because the algorithm pays too much attention to a simple data. It has a fluctuation between two measurements. It's quite impossible, even if you just perform out the measurements in a row, one by one, using the same multimeters, the same device, you have some distortion, some error. Okay, you have fluctuation, like in voltage or in current, you have fluctuation. If you have too much data, too many data and the model is overfitted, it pays too much attention to some distortion. It's also bad behavior of the model because it is too good for the data in the training set. So it does not possess the generalization capability. And the most important element for AI algorithms, one of the most important elements, is to possess the generalization capability. So we don't have to provide some information at the input. The algorithm should also, if some data is between the previously provided data, it should lead to the concrete and correct result. Okay, that's how the AI model should work. So this is overfitting. That's another issue. So to conclude, under and overfitting, a model with high bias is limited from learning the true trend and underfits the data. A model with high variance learns too much from the training data and overfits the data. The best model is in the middle of the two extremes. So the best model is in the middle. Underfitting, overfitting, and the correct model is here. You can see it very clear on the three pictures. Okay, so in the middle is the best model. It approximates the data in the best way. I think you can agree with this, yes? So in the middle. So that's why you have to play with different algorithms, different parameters, and you must know how to evaluate the result. The recall, precision, and X-score is important because based on this information, you can say whether the model has appropriate structure. That's all for today. See you tomorrow in the morning at 8 o'clock, subsection number 1. And I don't know whether we meet in this room or another room, Professor. In this one? No? Which room? You will send me information, yes? Okay, thank you. So it's another room. And 8 subgroup number 1, then subgroup number 2. So that's all for today. Tomorrow.
Excuse me, President, and I think this position making the false negative. In the red.
But I talked to this, your colleague. Yes, it's right because it's it always depends on where are true labels and predictors. The predictors are here. So we call 0 as a true positive. Here is true positive.
Yes.
If 1250 is true positive, so this one is false.
Oh,
Positive. False.
Never. I think this is convert of this matrix and think this string convert, and I think this one is false negative and using. I think it's the correct answer.
That's false positive.
False positive
Because you have positive over here. That's a false negative. Because you have negative here as a true label. And here is the predictor. It's upside down.
It's negative or positive subject to the true labels.
Well, zero means, in this case, zero means true.
Oh, true.
True. It's not false. Because very often zero in your brain is like a negative value and one is positive or true. Because for digital circuits, you have 0 and 1 logic, Boolean logic. So 0 is false, 1 is true. Over here, 0 represents the state of an object, automation object. If there is no fault in an object, we say it produces 0 at the output. It does not produce any signal. So that's why the true positive is indicated by 0.
Okay.
Okay.
Thank you.
So the object, you have to think it's not a number, it's the state of the object.
Like double and tag.
Yeah.
Oh,
Yeah. It's the state of the object. Yeah.
Okay. Thank you. Thank you very much.
Thank you for your attention. I invite you to the next event during the Industry 4.0 week. See you!